So I want to thank everybody for joining us for our Architecting for the Cloud Breakfast Seminar. We really appreciate you guys coming out. I was a little worried as the flurry started to go, but luckily, I think, maybe under a couple of inches for once in this winter. As you know, we have two guest speakers here, John Treadway from Cloud Technology Partners and South Proctor of NuoDB. Just spent some time learning about their experiences and what they're hearing from their customers and the implementations that they've seen. It is meant to be an interactive session, right? So we will have a Q&A at the end, but if you have something to ask or you want to interject something, feel free to do so throughout the session, and we'll kind of go from there. And with that, I'm going to go ahead and turn over to John.
Great. Hey, thank you very much. Appreciate it. Good morning.
Good morning.
Wake up, everybody. Good morning. Back here, move that. So let's see. I need to figure out where my slides are now, right? Because that's not on this.
Just go next. No, just go next, John.
Next? Okay. Because it actually didn't show that. Oh, there it is. Okay. There you go. It wasn't showing it on here. All right. So anyway, John Treadway with Cloud Technology Partners. How many people know who Cloud Technology Partners is? Okay, a few of you do, which is great. That's my contact information. It's on the slides. It will also be available on the last slide, and you can get it through Larita and the team here. So CTP is a company that was founded about 4.5 years ago, and all we do is work with clients on cloud computing projects. And we're a professional services firm. We do everything from strategy all the way through application development. We do DevOps, we do deployment, implementation, we build clouds for people. It's a whole range of services. We've done over 150 engagements, 100% referenceable. We are big partners with Amazon as well as with Google. And we have a lot of other partnerships that we don't spend as much time talking about. And a very experienced team. So the things that really make CTP kind of interesting and unique in the market is that we are not like a busload of 20-year-olds. We are actually a minivan full of 40-year-olds. And so people with a lot of experience doing a lot of very complex mission-critical things in their careers. And so our focus is on solving kind of the harder problems. And some of those harder problems are how do you deal with applications and architecture in a cloud context, and what's new, what's different, what changes. And that's what I'm going to talk about here today. We also, all we do is cloud and cloud-related things, so DevOps, which is one of the automation components that drives into the cloud, as well as cloud architectures and so on. And we've got some of our own technology that helps us actually deliver projects more quickly. So this is actually a Netflix diagram, but applications look differently in the cloud, new applications from people that are doing the big cloud projects. And one of the things that I always like to emphasize when talking about something new is that the typical model for innovation in IT and technology that we're all involved with here is that the innovation starts with the large non-traditional IT organizations. So a Netflix, a Facebook, a Google, Amazon, and so on, Salesforce, they do things differently because they have to, because the scale is different. And what happens is that we get to learn about all the things that they do and then bring those back and do what we're doing, because we're not, a few of us are at the scale of a Netflix, but that doesn't mean that what Netflix does doesn't apply to us, or doesn't have to apply to us. So this is, all the connection points, all the distribution, all the servers, all the modules, all the services, and a very small component of that in a Netflix architecture, and so we're going to get into the details. The pre-cloud application model is something built to run on a single server or a set of servers in a single data center, on servers that you control, servers that you own, hundreds of servers that you've got, and an infrastructure that you pre-provision for peak capacity, right? The typical model is I know that for this application, my peak demand is the holiday season. I've modeled it out. I'm going to need 50 front ends, and I'm going to need 13 middle tier servers and a cluster of database servers. And so, in order to meet my demand, I provision. I put a little bit of margin on that. I provision those tiers at that level, and I leave them running pretty much all year long, which is really expensive. And I actually had built it's funny, I built kind of something, as cloud was just getting started, I built a photo processing business that was very cyclical, very seasonal. And I was running in a data center here in Somerville. I had 30 terabytes of storage of people's photo images. I was doing this as a service to Polaroid and a few other places. But basically, I was paying my internet bill and my server lease costs and everything every month. And in January, those servers were so quiet you could hear a pin drop except for the disk. But they weren't doing anything. They were at 0.0002% utilization. Right? In November, they were on fire. Right? There was smoke coming out. So that's what you don't want to do, is have everything pre-provisioned for peak capacity, but that's the way that things have been done. And in corporate enterprises, we still see this all the time. We work with clients everywhere from as large as GE down to venture-funded startups. The startups don't do this, but the big companies, the big banks, the big enterprises that we work with, still a lot of their applications are pre-provisioned for peak plus some risk factor of capacity. Right? They use a centralized database, a database that sits in one place, and then there's a backup of that database, or a synchronous copy or an asynchronous copy of that database somewhere else. But the database becomes, some of you may have heard the term data gravity, but it becomes basically an immovable object at some point when it gets large enough, and it's really, really painful. And we assume that when we're building applications, typically, that we're building it to a level of resiliency in the infrastructure tier. Meaning, I've got redundant NICs, and I've got servers using enterprise VMware features where if this server fails, everything's synchronized to another server, and everything just runs, and I don't even know it, and it's easy. And so I've got high availability in the infrastructure tier, and so my application doesn't need to be aware because it just keeps running. And so that's kind of a typical model. And then I often build applications, especially kind of in the early days of distributed client server, and there's a lot of those out there still, distributed web apps, that are built in large monolithic code blocks. As a matter of fact, I would venture to guess that some people in this room still have a lot of applications or know of applications that are pretty monolithic in terms of their overall architecture pattern. So that's kind of the pre-cloud era. So I'm going to go through some old way, new way. I'm going to get through these slides pretty quickly and talk about some examples. And I'm breaking this down to assumptions, architecture, and operations. Just high-level bits here. So the old way, from an assumptions perspective, is that infrastructure is resilient, and therefore I don't need to worry about my app because the SLA for operating my app is managed by the infrastructure team. The new way is infrastructure is variable, resiliency is not guaranteed. So, that's now your responsibility as the app owner. Infrastructure is pre-provisioned or infrastructure is elastic, right? So the old way, the new way. Infrastructure drives scaling, meaning that I look at server utilization, CPU utilization, disk usage, swap, all this kind of stuff. I look at all those statistics, and then I decide whether or not I need more capacity. Whereas now the new model is I need my application to be aware of whether or not it's meeting its objectives, and if not, it needs to call for more resources as opposed to waiting for the infrastructure to realize that something's wrong. An example of that would be my goal is to check out a cart in 10 seconds or less, right? Now, how does that translate to CPU utilization? It's really hard to translate that, but I can actually meter whether or not a cart transaction completes in 10 seconds or less. And if it's not completing in 10 seconds or less because I'm doing lots of them, it must mean that I need more infrastructure to scale. So tell the infrastructure to give me more. Don't wait for the infrastructure to say, hey, you've got a problem here. Because the thing you're metering in the infrastructure tier may not actually be the thing that's causing the slow performance on the application tier. Right? Disaster recovery methods. I'm going to have disaster, and then I'm going to have recovery. So I talk about recovery time objectives and recovery point objectives. How many transactions can I lose? And I want everything to run in a way that I can actually recover from a failure of my site or my servers in another location. Because, you know, what happens if the cable is cut to my data center? I need my application still to be running, so I'm going to recover from that failure. The model of a Netflix or a new modern application is that disaster recovery is stupid because I've got so much going on, so much data happening, I could never possibly keep up. I want to have continuous availability and continuous operations. So a whole data center fails and nothing happens, nobody notices, right? If the tree falls in the forest and it doesn't make a sound, did it really happen, right, that model? Well, if the data center fails and no users are impacted or their impact is very small, did it really matter to them that your data center failed? I mean, it matters to you, but it doesn't matter to them. And an example of that is there was an Amazon, God, what was that, 3 years ago? So the big outage in the US East region related to an improperly configured network router that basically loaded up all of their block storage devices at Amazon in the East. So every block storage device, their elastic block store in Amazon, got absolutely plugged full of data, of crap data. Basically, it was replicating between itself all over the place because somebody misconfigured a single network device. The result was that anybody that was running in the US East was offline for hours. And if you, which basically is effectively a disaster. The data center was offline because you couldn't write the disk, right? Nothing would happen. So US East went down, and people that were running in US East and only running in US East were impacted. They were out, and they had to try to figure out how to recover. Well, a lot of those people didn't even have a recovery strategy at all. Netflix, on the other hand, was running in US East and US West. And so when the data center crashed in US East, they had a slight service degradation, and they spun up more servers in West, and they kept going. Quora and Reddit and a number of other high-profile sites were down for half a day or more. So that's kind of what changes. All right, architecture is different. You know, we've always been told, you know, don't build large monolithic apps. But you know what? For the most part, in the old model, they've tended to work. But today, we talk about microservices, and I'll get into a little bit of detail about microservices in a bit. That's decoupling your application into small services that you run and consume as opposed to a big monolithic app. Functions that are highly dependent are co-located, meaning I put things together that need to run together versus having them globally distributed, which is kind of more of a new way. I can run things across multiple data centers. Application portability is hard. I can't move my app from one place to another because my data is stuck in one place and it's hard to move the data, or I've got dependencies. And now with distributed database technology, as well as with things like Docker, moving applications between data centers is actually relatively easy. In the old way, applications are operated by my infrastructure and operations team. In the new way, applications are operated, the services are operated by the people who develop them. This is a big change, right? How many of you are in development teams where you're responsible for the availability of your solution and you get the pager call at 3 in the morning when it doesn't run? A couple of you, right? So you know what I'm talking about, right? Versus relying on the infrastructure team to do this for you, right? Now the developers are on pager. The developer gets a cell phone call at 3 in the morning. Your service doesn't work anymore. You need to get online and fix it, right? That's a whole different model, and that changes a lot of things in terms of the way you build and deploy apps. Operations, right? VMs are, and servers are pets. If a server fails, I want to nurse it back to health. I'm going to repair it. I'm going to fix it. I'm going to try to get it back and running. In the new way, a server fails or a VM fails, I just kill it, right? It's not a pet. I don't need it back to health. I'm just going to put a bullet in its head and go on and get the next one going, right? So that's the old model of, you know, pets versus cattle. And also, like a VM is a VM is a VM. Like my app runs in a VM here, it'll run in a VM over there. The problem is that that's true if the VM environment and the infrastructure underlying it is similar to the one that you're coming from. So you're going from an enterprise data center to Amazon. your VM is actually very different. You might actually get the code to run, but operationally it's going to be very different. And so, and clouds are like snowflakes, and no two are alike. So you have to model the behavior of your applications and not assume that just because it runs in a VM, everything is hunky-dory. It's not. Business as usual operations patterns can work in a cloud, like the way that I do things. I have documentation, I have a process, and somebody does a service request, and the InfoSec team provisions all the agents, and the operations team provisions their monitoring agents. And all this happens manually, and days or weeks later, my VM is ready, right? That's an old model that still exists, and most enterprises actually do a ton of that, still manual processing of machines, even in something that they call their private cloud, right? Private clouds that don't provision automatically every layer of every piece that you need to run your application in 5 or 10 minutes or less are not clouds. Applications run in a data center with maybe a backup versus applications span data centers, regions, and even borders, right? So a single application can operate and run across borders. That's a new model from an operations perspective. How do you handle that? How do you deal with the complexity of managing that environment? So that changes as well. So let's talk a little bit about microservices. There's a lot of things going on there. People have different opinions about are they good, are they bad? The bigger applications, the things that you might be doing are decomposed into services. Service teams building services. A service might be an account lookup service, like I want to look up account data. So I build a service to go look at account data. And then another application needs account data, so instead of going to the database where all the account data is, it just goes to the service and says, return me the account data, right? And then what I do is I have that connection be very loose. I put it behind a RESTful interface, and I say, hey, connection, hey, service, get me this, and I send a RESTful request, and I get back JSON back. I can parse that, and I say, okay, now I know what the account data is. And by the way, because I've done this over HTTP, I now can put a load balancer in front of it, and I can elastically scale it, and potentially using IP routing and load balancing, run that same service in 5 different places, in 5 different geographies around the globe. So the account lookup function could be running, the same account lookup function could be running in Tokyo, Boston, Sunnyvale, and Germany, all right? And returning the same data. And so what you do is you load balance across all of those globally, right? So the one that can return the account data fastest is the one that you go to. And if one of them fails, but a microservice fails, the guys at Netflix actually like to talk about minimizing the blast radius. The smaller the service and the more copies of it that you have, when one fails, it's kind of like a ladyfinger, like a little small firecracker going off, versus an NA big boom, right? That's the kind of stuff you can do with services and service architecture. It's really important to think about how do you deal with these requests asynchronously, because when you're making a model like this, and you have to think about your transaction flow and integrity of your transactions when you're doing this, so then you need to start to build in logic to track state of a transaction. But if you can do that, then you don't have to wait for, you can do things and not wait for a response and continue to be doing things in parallel, versus I have to wait for a response. If that service fails and another instance is spinning up, it could be 3 minutes before I can get that response, then my system is down and it crashes. So the kind of takeaway on microservices from an architecture perspective is that they're really, really powerful, and you should do it. But managing a collection of services, of service instances, even for a single service, and making them operate and monitoring, I've got 50 instances of my account lookup service running globally, and I need to know what the health of the service is, not the health of a single server, then I need to track all 50 servers. And I need to know which ones are running inbound, which ones are performing quickly. So it's complex, but if I do it the right way, then it gives me a lot more scale. It also allows me to be very agile as a developer. I can update a service very quickly versus updating a whole model with a gap. So I could release service updates 7 times a day and put them into production, because I'm only dealing with my own stuff. I do need to make sure that I get my, that the data coming back is consistent. But if the interfaces haven't changed, and I'm making it more resilient, or I'm making it faster, I speed up a transaction because I changed the index on the database, those types of things you can do very quickly and not have to take down the whole application. But it's complex. All right, horizontal scaling from an application perspective, it's very critical, but it's hard. And I'll give you an example. So we built a piece of software that we built for a client. We did it as kind of a single instance. It was a little prototype, just ran inside their data center. And then we said, well, we want to make this a elastically scalable application, SaaS-based application where when more people use it, it'll spin up servers. And it turns out that that sounds really great, but it's hard to do because if you've got a new application you're building, you can build apps to run that way very easy. But if you've got an existing application and you're trying to take something that doesn't know how to be elastic and make it elastic, you're re-architecting a lot of code in that application. So it can be pretty complex. And one of the important things about elasticity, this is kind of the opposite of what everybody thinks. I want my app to be able to scale to hundreds of instances when I need it, right? That's great. But going back to pre-provisioning versus elastic provisioning, what you really want is when you're not using it, what I wanted in January of 2006, when I had my photo site running before Amazon was really up and running with their cloud, is I wanted to pay less money in January, but I couldn't. What I really wanted to pay was almost next to nothing because, again, there was nothing going on in my servers. So the same thing happens in a cloud. It's not how big you get, it's how small can you get. And how quickly can you get small when the demand goes away. Making that work is really, really hard. Right? Scaling up, scaling down, putting the rules in, putting the logic in the application, dealing with the fact that I might have started a whole bunch of instances, and now that I need to collect the garbage because I'm no longer using them. Think about it, as a programmer, you know about garbage collection, and Java handles that for you, supposedly. What about garbage collection in your VM farm? Because there's a lot of garbage in your VM farm, internally or externally. So how do I collect the garbage? How do I know which instances are no longer running or needed and get rid of them? To get it also, you want predictable performance. In the old day, you had the pre-provisioned infrastructure. Everything was running in your data center, and it was on a network that you controlled, and you knew what the QoS was on the network. You knew what the IOPS were on the server, on the storage. You knew what the CPU utilization and load characteristics were of the servers that you had just bought from HP, right? So I could predictably know what my server was going to do in any kind of given situation. You spin up an instance on Amazon, and you spin up lots of different instances, and you may end up with a whole bunch of EC2 smalls right on Amazon, that each one of them has very different performance characteristics, because one's on an old box, one's on a new box, one is on a network that's getting hosed by a noisy neighbor, one's on a network that's quiet, right? You've got other workloads on that machine in other VMs, or maybe you don't. You don't know. So being predictable about performance is really hard in an elastic scale-out world. So you have to test for predictability. So test it under lots of different scenarios. And the key is, what's the upper and lower bounds that you're expecting? And when you get out of the upper bound, when things start to go slower than you expect, you need to do root cause analysis to figure that out. Things like state management, right? You hear about this, I need a stateless application. What does that mean? At the end of the day, what it means is that if I make a request of a server and it gives me a response, and I make another request to that same server and it's no longer there, and then the only way I can finish this transaction is to get information from that one server, I'm dead, right? And Amazon instances go down at scale all the time. You should expect that in your cloud, that things may go away. So you can't manage state in the server that it's running. You can manage state in the database and reconnect. You can manage state in the client side, so put state variables in the URLs in the page that you're posting from. But state management is key, because then you can't scale out elastically or scale back in. You're killing instances because of you don't have demand. You don't want requests to go to those instances and get hung. And bad things happen to good VMs, right? So good VMs look really good today. It looks really great when you spin it up, but all of a sudden you start to see degradation. How do you deal with that? When you're doing elastically scalable applications, you need to have real-time analytics on the state of, and predictive analytics on the state of your virtual machines, because they do degrade. And then what do you do when it degrades? You just restart it. Start it on a new one. Resilience is really where the application owns it, right? So an example, let me give you an example. We were working with a client that had an application that was typically, the application itself didn't know anything about whether or not it was available or not, right? It was just code, and the code just ran. And I didn't need to know anything about it. So part of the application was relying on another part of the application being there, and they just assumed that the infrastructure would take care of that. And they put it out in the public cloud, and one of the instances failed, and the application hung mid-transaction, right? And every user was shut out, because it was a single service without load balancing, without a whole bunch of other things. It basically died. So what you need to do then, as an application builder, is actually, you need to know whether or not the things that you depend upon are there, and what their performance is, which means that your application needs to be infrastructure and service aware. So, and not only that, if something goes bad, the application needs to be able to make a request to start another instance of something. So, the service doesn't always have to restart itself, because it may not know that it's dead. But if you are relying on that service, if you're making a call to that service and it doesn't respond, you need to know how, your application needs to know how to tell some other system, I need another copy of that instance because I can't perform this transaction unless I get it. So resiliency is about falling down a lot of times and keep getting up, right? You keep going, you keep going, you keep going. You have to build that into the application tier and get out of thinking about the infrastructure as being resilient. And then globally distributed. This one's a big one. If you start, we talked about Netflix going across data centers to be distributed, but these days it's more than just east and west. I've got clients that are all over the world, right? I've got latency issues. I want a great user experience, so I do things like in the old days. I would cache some content using Akamai right around the corner here, or some other content delivery network. I would cache my stuff, and then I would be able to at least give some of the responsiveness that I need, but I still have a single database in the back that was doing everything. And if that database was in Tokyo or in San Francisco, my client was in Tokyo, the back and forth could actually be really long. So now I distribute my application code, so the application runs on a distributed basis, so I have copies of services. I look at the performance of all of my nodes. I route to the best performing node, right, that's closest to me, that has the quickest amount of hops. Right? How many of you used speed test from Ookla to figure out whether your Wi-Fi provider is working? Right? What does it do? It goes and it pings all the hops near you. It says, I'm going to use this server to do the test, right? This is the best one. You need to be doing the same thing, pinging your services, figuring out which ones are giving quick response times, because maybe, just maybe, something is slowing down that connection, that one route that you're using between India and the US, right? And you want your Indian users to get access to that application. So global distribution is hard, and it used to be a lot harder because distributed databases were a lot harder. So this basically leads me to the new way of applications, which is that they're run across data centers, geographies, and et cetera. They run on servers in the cloud. You provision when you need them. They use distributed cloud database technology or techniques. Availability is built into the application, and it's, microservices, RESTful interfaces. It's all different from the way you built it 10 years ago. And a lot of the applications that you may be working with were built or architected 10 years ago, and it's a lot of work to go through that and figure that out. So that is, as quickly as I can do, conversation about the new architectures for the cloud. Yes?
Just curious, on one of your slides you had cloud that said microservices is not the same as a service-oriented architecture.
Yes. So microservices is not the same as SOA, or service-oriented architecture. Traditional model of SOA, right, and the old kind of distributed object and Corva models before that as well, was that I've got like an enterprise service bus, some mega bus that I put things onto and I take things off of. IBM MQ series, before that it was Kix. It was like, some transaction manager, some kind of a queuing system. TIBCO had their model, right? So that was the model, and that's kind of a traditional SOA model, is that I'm going to use an enterprise service bus, I'm going to put things on, take things off, right? That model that basically puts a whole bunch of the onus of availability and performance into the service bus, and then the service bus becomes potentially your choke point and your problem. So and also the whole idea of like service discovery and UDDI and all the stuff that we've long forgotten about because nobody actually does it. The new model is I build out services. They are RESTful. They're sitting there waiting for requests. You make a request of a service through a URL, and that URL is routed using DNS, and it's routed to a load balancer, which tells you that this one's available and whatever load balancing scheme it is, and the response comes back. All right, and then I move on. I didn't put it on a service request broker, right? What I did was called the service by its name and said, give me back, just like I can talk to you, you talk to me. I don't need to actually go through, some network to talk to you, right? We can talk to each other. And you saw that chart on slide, I think it was slide 2, but if I can bring it back. Anyway, that Netflix thing, all those connections, that's what it looks like. Services today, microservices, look like network diagrams that are highly distributed and not centralized. Other questions?
You talk a lot about the nature of the new app that will take advantage of the cloud infrastructure and its services, maybe shortcomings and strengths. I'm just curious, is your business spending more time with folks building those ways, building under the new methodology, or are you spending most of your time limping in with the apps that are trying to make stepwise transitions to the cloud?
So that's a good question. So it depends on the client, right? We've done a lot of work with like startups building new applications for them, or enterprises that are building new greenfield applications, and which is great because we can start with these techniques. We can build apps this way. But a lot of times we're coming in and somebody's saying, I want to get out of my data center and I need to move all this stuff to Amazon. Tell me what I don't know. And so we go through and we do a review. We look at the applications across the whole portfolio that are in that data center, and then we have to decompose them and look at which ones are more modern, which ones are not. We talk to the architects, and then we figure out which ones are going to have a problem and what's it going to cost to fix them. In some cases, it's replace it, don't move it to another data center that's more like the old data center, or we get into doing refactoring. So there was an ATM company, one of the big ATM manufacturers. They have applications that they deploy on-premise for their banking customers that do things like marketing. Like if I want to put a marketing message into my ATM, there's a little application that your marketing team will use to set those messages up, right? So what they wanted to do is get out of having to deploy those. A couple of them were very large and very complex monolithic, requiring 20+ servers to deploy into a large bank, and so they could only sell that to their tier 1 banks who wanted that. All the community banks couldn't do that, and it was not multi-tenant. So we had to actually go in and say, how is this application going to run? We're re-architecting it for multi-tenancy, but also to run in the cloud. And the third requirement was we were running on a modern platform as a service software layer, which meant we were basically changing everything. So we spent a lot of time doing service decomposition, re-architecting the core components, basically to get that to run. So it's a mix, depends on the client, but we do spend a lot of time doing both. Other questions before I turn it over to Seth? No? So, we're back to the beginning. I guess I'm back to the beginning. We'll go.
Thank you, John.
Thank you, John. So I feel all right, so I'm Seth Proctor, the CTO at NuoDB. I feel a little bit like this is the point in the roast where the guy gets up whose jokes have just been used. And he's like, was it like Hetty Youngman who used to get up and do the thing with the cards, be like, done that one, done. Maybe. Okay, that's too early. Too early for Friars Club jokes. Okay, so at any rate, I want to talk about kind of two broad topics this morning. Obviously, one thing I'd like to talk about a little bit is the database specifically, where some of the challenges are when we're thinking about cloud architectures, some of the problems that John was talking about, why the database is kind of uniquely challenging in making the system scale. The first thing I want to do, though, is talk a little bit about what we're really talking about with architecture in the cloud. I think John talked about a lot of the really pragmatic, really real problems that people have and think about in cloud architectures. I'm an old school systems guy, and to me, I like to step back and say, when we're talking about cloud, we're really fundamentally rethinking how we build applications. And that question about, SOA versus, microservices versus whatever else, to me, that's not about what's the application doing, what's the whatever doing. The microservices thing to me is important because that's thinking about the world through microkernels, right? You build a little thing, you layer on top of it, you understand how the components fit together, you build from abstraction, you understand things will fail. Resiliency, I'm going to talk about as well, totally important. My personal view is resiliency comes in several stages, and if you push it all on the application, you're going to be in trouble. Then again, my personal view also is microarchitectures are great, but don't do 7 pushes a day of your live application. That is, I know, call me old, but like, you know what, totally insane. We don't, in the enterprise world, really just do yourself and everyone you love a favor, and don't do that. So what is unique about cloud, other than like all the hype and the interest about it, right? I think stepping back and trying to summarize what John just covered, there are a couple of important things that I think cloud means to most people, right? So on demand, right? This notion of being able to scale out, and as John said, be able to scale back when you don't need capacity, right? If you're on demand because you care about capacity, if you're on demand because you care about availability, that's really important. That notion of flexibility is really important. And sometimes it's about public infrastructure. Sometimes it's about your private data center. But there are all kinds of different platforms, all kinds of different APIs people use. And so inherent in cloud architectures is really thinking first principles about how you do dynamic provisioning. Right? So it's not just the ability to be able to bring up an instance, but like, how did I know to do that? Who was able to talk to it? How do I think about those pieces? That gives you flexibility, right? We kind of like seeing flexibility, and that's kind of a hallmark of cloud architectures, is the ability to pick the hardware and the software that you want to use. A lot of people kind of bucket that in, I can run on commodity, right? I no longer have to buy the big iron. Lots of people who build clouds, especially private clouds, are still running on massive scale systems, right? So cloud is not uniquely commodity, but the ability to harness commodity, the ability to harness hybrid infrastructure, to run across different clouds, to run different operating systems, to use a mix of cheap disks and really high-end disks. I think that's something that people really see in all cloud architectures. And it has to be simple. Right, simplicity is something that sometimes I think gets lost in the shift, right? As John is going through and talking more and more, there's this piece and there's that piece, and you've got to think about this, and there's microservices, and there are all these little things that are running around, and that's great. And then suddenly you go, what are all these pieces? What do I have running, and where do I have them, right? And so I think as people think about cloud architectures, right, one of the things that's really important that you see people focusing more and more on is the monitoring aspect, the management aspects. Right? This isn't about the application, this is about staying sane in this world. Whoever it is that's going to hold the pager, we'll talk about the pager later. I'm really sad, by the way, I recently was like talking to a bunch of college students, I made a joke about the pager, and they all just gave me blank stares. I was like, come on guys, really? Like, really? So I don't know, we're going to have to come, I don't know what the new joke, like, I don't know what the new term is going to be, but like when someone coins that, like that's going to be a thing to get on the web quickly.
They all use pager duty.
Sorry?
They all use pager duties.
So I was on a panel with the CTO from PagerDuty this fall, and he's a really cool guy. And he actually made the same comment to me. He's like, a lot of my people don't know where pager is. It's really sad. And so to get all these things, right, to have flexibility, we think about cloud architectures being things where kind of that monitoring aspect is part of the architecture. It's not off to the side. And that means you have clear APIs, right? John talked a little bit about this. You have the APIs to understand how to do all these different tasks. You have your services, you have microservices or larger services, you have a way of doing provisioning, you have ways of doing monitoring, you have ways of building automation around this to further simplify things. And I think we all care increasingly about resiliency. I'm not going to talk as much to this point right now. I'll talk a little bit later about my views on resiliency. I'm also going to say for folks who have in front of them that 25-page white paper and are looking for a slightly shorter read, we just came out with a new release of our software this week. We also put out a white paper that focuses entirely on continuous availability. Resiliency is a really key topic. It's only like 10 pages. So highly recommend going and checking that out. But I think that topic of resiliency is really important. And I think resiliency really is a word that means a lot of different things to different people. If you go talk to people in the telco space or in aerospace, resiliency means something very different than when you go talk to someone who's application designers. And I think that's what's really interesting about where cloud architectures are taking us, right? Why does the dialed IO, another joke that doesn't work anymore, why does the dial tone always show up when you pick up a phone in your house? Right? I mean, it's always there. And the reason is because telecom's designed around resiliency, right? Resiliency means things will fail all the time. And it means you can't have downtime when things fail while you're swapping over. It means things always have to be running. It was John's example, don't just run at Amazon East. Right? That mindset is something that I think is increasingly becoming critical, and that's why this whole discussion is important today. Why all the effort? Why care about these new architectures? Right? I think you get fundamentally some important new capabilities, and you're willing to think about the world from this different point of view. Again, John touched on a lot of these, right? Greater capacity. We like being able to have that capacity on demand, but generally being able to access greater capacity. Cost effectiveness, really important when we're talking about cloud. Higher availability, general and better failure handling. That comes back to that resiliency thing, but that's also about having resources available on demand so that you can react to things. That's about having APIs and monitoring built into your architecture view, right, so that you really can react to failures really efficiently. And increasingly, as people think about applications being global, as a baseline, not as a nice to have, right, as a requirement for various reasons, I think that idea of running in multiple regions for high availability, running for low latency, that's really one of the motivators for why we're willing to go through all this effort. And it is effort, right? I mean, cloud is awesome. It's buzzword worthy, and it's got lots of fun things in it. And, you know, people are talking about all the great stuff in clouds. It's a lot of work, right? And there's the view that like cloud is you kind of hack together your RESTful this and your JSON that, and you put things together and you've got a cloud. When you step back and you're thinking about architecturally, this is a complete shift, right? We did the mainframe, we did client server for a long time. What are we doing right now? Well, what we're doing right now is the thing we've been doing for 10 or 15 years is starting to take distributed computing ideas and make them mainstream, right? Distributed computing is hard, right? Probably a lot of people in this room have worked on distributed computing projects over the years. They're complicated, they're difficult to get right. We'll talk about some of those challenges in the next few minutes. These are not simple things to build, right? And you can build kind of a nice ad hoc, throw things together, and then get a lot of redundancy in the system because we assume we're going to get a lot of things wrong. When you're thinking fundamentally about the architecture, there are a few things, though, that are really critical. Lots of failures will happen. You know, commodity is great until you realize that commodity probably means more failures. Lots of things running in a heterogeneous environment is great in terms of flexibility until you realize it means more things will fail in more unexpected ways, isolated in different places. That's a challenge. It is very hard in a distributed system to get a single logical view of the world, right? And I don't know how many of you have deployed 200 or 300 servers and realized the only way you could sort out what went wrong when 40 of them were interacting with each other was to look at the log files locally each of those 40 systems. But like you're sitting there 2 in the morning and you've got 40 terminals up and you're trying to remember like IP whatever and this one and that one, and like one of the 40 machines didn't have NTP configured correctly, and you're like, oh my god. So that view, that's a real challenge. And the security model and the data lifecycle model becomes harder, right? When you have data sitting in one place, you can kind of come up with a security model, an access model, you can define your users, you understand something about how the data got into that server and where it went from there. As you start building up this ecosystem of all these connected components, trying to track how that data moved from one place to another, who had access to it, and what form it's in now, and can you even talk about the life cycle of that data? That becomes really, really hard. For a lot of people, that's actually a more important scaling challenge than things like throughput or being able to get at CPU. This is actually, when you go down Wall Street, for example, you would talk to big banks and you say, where are your real scaling challenges? This is actually a huge scaling challenge. It's nothing to do with performance. And everything else about distributed computing. And if folks in here haven't gone off and read fun distributed computing problems, like you're looking for something fun to do this afternoon, it's Thursday afternoon, it's kind of dreary out, go Google the two generals problem and sit down and read that and think about it. And I guarantee it'll be, I don't know, it'll be entertaining. You'll be sitting there screaming like, damn it, Seth, why did you do this? But the takeaway, right, from John's talk is that fundamentally, as an industry, one of the things we're really good at is we're good at solving pragmatic problems and saying, well, maybe I can't come up with all these great, pure, elegant architectures, but I kind of understand what the problems are I want to solve. I kind of understand that these are challenges facing me. And I kind of need to get something done in 2 months because it's October right now and Black Friday is right around the corner. And I understand I need a solution to that problem, right? And that's kind of what John was talking about, is we really have come up with good solutions for a lot of the layers that make cloud systems work today, right? So load balancers and name servers are really good at direction point. We're pretty good at building out horizontally scaled, independent, stateless app servers, web servers, and all that core technology that lets the application layer scale. We kind of understand caching technologies. We deploy CDNs like crazy, right? I mean, Netflix is the canonical example in almost every cloud discussion, right? I mean, Netflix represents, well, like a third of the internet data. I mean, it's crazy, right? And a lot of it's in CDNs. And increasingly, CDNs are places where people are putting not just kind of streaming data, but things that are kind of semi-stable, things that change, just not with frequency of every second. And down at the storage layer, we're pretty good at understanding how to harness, commodities disks or higher-end disks, NASes. We're pretty good at understanding how to build out object stores. We kind of understand how to build these things that hide the fact that it's actually a lot of spinning disks or a lot of SSDs into aggregate pools, right? The challenge for anyone in this room who has done this before, probably you've experienced this too, the challenge is the database. The database is the thing that doesn't just naturally scale in this world, and when we're looking at this list of challenges here, right, it's the database piece that really suffers the most when you try to understand how to map these issues. Why? Right. Well, let's go back and think about traditional RDBMS architectures, right? So you go back to the late 1960s. There's this guy, Cod, sitting around, and he's like, I got this idea for a data model. I'm going to write down a whole bunch of rules, and you can argue later about how many rules he wrote down, but I'm going to write down some number of rules that talk about what transactional consistency is, what a programming model would look like to work with data in a consistent fashion, right? And then you go to the early 1970s, and a bunch of guys at IBM are told to go take those ideas and build a system, and they go build something, maybe not what Ted Cod described, but they go off and they build a database called System R, right? And it turns out in the 1970s, disk was spare. It turns out memory was small. It turns out systems couldn't do a whole lot. Conveniently, it turns out we also didn't have a lot of data we needed to put into a database, so that was kind of sort of okay. But they looked at this problem and said, how do we build a system, right, that will solve the problems that we need to give us something like this relational algebra that Ted Cod talked about. And so they built something that we tend to call kind of a vertical scaled system, right? They built something where they said, let's take data, let's chunk it up into pages, let's lay those pages out on disk in a very fixed fashion, such that it's really efficient to get a single page off of disk into memory. It lines up well with the cache lines, it fits well into how we have memory chunked up. Essentially, we reinvented virtual memory. And let's lay it out on disk such that when we're doing sequential reads, the disk head kind of tends to just go right across those pages in a natural fashion. We've optimized those resources as effectively as possible. That's great. And that system will keep scaling as long as I'm on a single machine with a logical disk that runs really quickly, that's directly attached to where I'm running things in memory, with a model to get between those two things very, very, very efficiently. All right, that's it. That's it. One version of what it means to be vertically scaled. You can put caching in front of this. It's hard to do it because the whole point of the original system R exercise, even though it didn't actually really have transactional consistency, the original idea was thinking about transactions, and caching tends to break that. But you can try to apply caching. HA, however, becomes really hard now, right? Because we're talking by definition about running in a single place. And if that single place fails, like John said, if that single place fails, you've lost your database, right? And that's kind of a problem, especially when we're talking about all these cloud ideas, right? But fundamentally, like when you fast forward, this is still what Oracle looks like, right? This is still what DB2 at its heart looks like, right? And you look at SQL Server from Microsoft, like Hackathon, has done all kinds of really cool things in memory. Oracle is doing really interesting things in memory. Other databases are trying to hoist things, away from this model. But they're still fundamentally predicated on this vertical scaled system that's about the disk, right? And as long as you're thinking about things in memory and things on disk, you're going to continue to have trouble to scale in this kind of cloud architecture world. There are also some other interesting side effects, right? Your schema ends up being really hard to change because your schema is encoded in every bit on disk, right? And so what have we done as an industry? We said, let's get rid of the schema. That's not really the right answer. It kind of makes things a little bit easier operationally until you actually want some data definition. It's really hard to harness commodity infrastructure in this model, right? Because again, commodity will fail more reliably. The whole value here is predicated on high performance between specific components. That's a problem. This is just not a model that is designed to do scale out in a cloud. What have we done? Again, pragmatism is one of our hallmarks as an industry. What are some of the approaches we've taken? Probably everyone in this room, since you're here and you're interested in this topic, probably you've tried one of these three approaches at least. Is there anyone who has not actually tried one of these approaches in real life? Oh, sweet. Okay, so I don't really have to spend much time on this. You all understand what I'm talking about, right? These are proof points that we can build cloud architectures, we can apply existing technologies, and we can solve some set of problems, right? We can kind of get by. You can replicate your data. You can say, I've got this database, I'm going to replicate data out of this database to another place. I can only write to it in one place, but I can read to it from something else. And if the system fails, well, probably most of my data is available in my replica, right? And probably most of my data is the thing that scares me the most because, like, I was having dinner a couple weeks ago with a customer of ours, and he just looked at me, and he's like, you have to understand, like, when the towers went down, we had infrastructure in there, the database kept running, and we didn't lose a record. Right? I mean, people care about these things. So they're like, probably, maybe the data's been replicated correctly, works for some people, not for everyone. Right? And it introduces read your own write problems, it introduces delays, and like when you can actually see changes, there are all kinds of other challenges. You can also shard your data, right? You can say, let's take the database and split it into lots of separate disjoint databases. And now you've limited what you can do in terms of your visibility and access model, because you can't run a transaction that spans those different databases. It's hard to relate them. Even if you're not running in a transactional system, there's still all kinds of questions now about when things are up to date, where, and what the visibility model is. You get more capacity, though. You do get more capacity. You get more disk, you get more throughput, you get more independent places you can work with. You also get more independent places that can fail. And if one of those places fails, now suddenly your data service is not complete. Right? You're missing a chunk of what your service should be able to do. So what's the easier approach maybe is just to get rid of consistency. Like, consistency is a pain, who needs it? You can do that. And it turns out as soon as you're willing to abandon consistency, things get a lot easier architecturally. Right? And so probably everyone in this room has gone through this and tried to understand what that means. Essentially, this is the view of let the application sort it out. The database is no longer a thing that is trying to optimize your problems. The database is no longer a thing that is trying to enforce some view of the data model. The database is now just a place where you put data and you ask for it later, and the application is responsible for figuring out was the data correct, was the data mutated in a correct fashion, am I seeing the right version of some data? You know, if something failed, what version of the data did I end up with? My bias is probably pretty obvious. Call me old-fashioned. I believe transactions were invented for a reason. They're there to simplify our life. They're there to help us in the face of failure. They're there to take much more complicated systems problems and make them simpler. I think this approach here is something we did not because we didn't like consistency, and not because we liked strange failures that leave our data in unknown states, but because building a system that does this is really hard. And what we want is we want all that cloud stuff we've been talking about for the last half hour. And so this seemed like a reasonable approach, right? The thing is, no matter which of these approaches you take, right, they each have, I think, very good aspects to them. They have real challenges and painful problems to them. No matter which approach you decide to take, you end up with a few side effects. In my mind, the biggest side effect, the thing that scares me the most, is that applications are now tied to your deployment model. Okay, and I'm going to say something that is really not cool right now. It's not in trend. DevOps, like, I'm all for the idea that developers understand the pain operators go through and understand the reality of deploying things. And I believe that every operator out there needs to spend a little bit more time understanding how to write real software and understand like why software engineering is a hard practice. You know, all that said, I think DevOps is a bug. Like, I think DevOps is a thing that we've evolved in this industry because we've had to very tightly couple how we do things like application development and data management. Because if you shard something, you need to know, well, it's 10 shards and here's where they live. If you're replicating something, you need to know, well, can you read your own writes? Where can you read? Where can you write? And if you want to change the way you're deploying your database, now you've got to change your application logic. And if you want to rewrite your application and make it scale, you've got to change your deployment model. And I think these two things should be able to evolve independently. You should be able to work on your application and evolve it and grow it, and separately you should be able to make decisions about your operations model. And by the way, that's the thing that starts to get you true resilience, right? Because if your core systems can fail in independent pieces and your application is unaffected, now your application doesn't have to have complex logic embedded into it about how to handle those failures. It just keeps running, right? And that's where you start to get the dial tone is always there when you want it. Seriously, the dial tone, the pager, like, we need to come up with a whole new set of metaphors, and if anyone's got ideas, like, yeah.
Just a question.
Yeah.
If application fails, how do you assume that the operational guy will know what to do with it?
I'm sorry?
If application fails,
Yeah.
I assume that the operational guys will know what to do with it.
Well, I'm not saying that the operator should be completely ignorant of what's running in the data center.
Or can they troubleshoot the failure?
Well, every environment, so DevOps is not a new, the idea of DevOps, the idea that I have an operator that understands something about the application is not a new thing, right? If you go to HP and you talk to the DBAs at HP, right? The DBAs at HP spend a lot of their time wearing pagers and reacting to application problems, right? They don't call it DevOps, but that's the same way they've run databases for like 20 years. I mean, there has to be some knowledge there back and forth, right? When something fails, someone has to know what that is. There are things you can automate, and then there are things where all you can do is throw your hands up and go like, I don't know, something failed, here's what I can tell you. A human has to get in the loop and sort it out. So that's always going to be necessary, right? The question is, how do you make more of those failures transparent? How do you make more of them things that you can react to automatically?
I'm not just reacting to your saying that DevOps is
The idea that there are developers, right, the idea that there are developers and there are operators, absolutely. The idea that they have to collaborate together, absolutely. To me, the DevOps movement that we're all excited about is this, like, developers and operators are like writing things very tightly together, assuming that like their stuff needs to understand each other. Sorry?
That's a best practice for the mission.
That's what I'm saying. That's right. It's not.
But that's not DevOps.
Well, I'll hang around afterwards. We can have a conversation about what DevOps is and isn't. As I said, that's an intentionally kind of provocative comment, but that's just, my card's out on the table. Other problems you have with all of these approaches we're talking about, right? One problem, you have more independent pieces. You've got more independent things that can fail. If I'm sharding my database, if I have lots of replicated copies, I have more independent things that can fail that will have a net effect on the system because they may now represent a gap in my data, right? Cassandra is a great piece of technology. It's really a great piece of technology, and it solves a lot of pragmatic problems, right? It is designed with an assumption that you can replicate each object a certain number of times, and probabilistically that means that the data will always be available, right? You can still construct failure cases very easily where suddenly you are missing a subset of data, right? That's one of those challenges that distributed computing problems always have to fix, right? And it's just, it gets more amplified, I think, when you're thinking about these kind of simple idea of let's just shard the database or let's just replicate it in some fashion. It also becomes much harder to interpret these failures, and you have much more complexity overall in the system. And John talked about global deployment, and to me this is one of those critical issues today that is, as I said earlier, is not a nice to have. It is where the industry is going, is that people need to run in more than one, whatever you want to call it, availability zone, region, data center, geography, kind of however you think about the world, right? People want to run in more than one physical location. Why? Obviously, disaster recovery reasons, availability reasons, that's kind of the first reason that a lot of people think about. Increasingly, I talk to people who are interested in distributing their applications because they have their users physically distributed, and they want to provide lower latency access to their users in multiple locations. Right, so that's another critical motivator. Third critical motivator I mentioned earlier has nothing to do with performance, right? It's just that there are security rules, there are residency rules, there are governance rules. There are reasons why you need something running in multiple locations because you are managing data that represents different users who have different laws associated with them, right? You may want that second one, that low latency access for your users because you're running a service in the US, the EU. But if your EU service has data associated with a German citizen, that data is supposed to say on disk in German. Right? So how do you reconcile those two things? How do you give that user low latency access to their data when they come to the US, but how do you still maintain those rules? All right, this is where kind of global operation stuff starts to change kind of all of the stuff we've been talking about for this talk. Because really what you start doing is you start thinking about these trade-offs between latencies and safety. Right? I want a database with low latency. I want to be able to solve these kind of hard access problems. But I also want to know something about where my data lives and where it's guaranteed to be on disk. And in the case of failure, where I can get at something. Right? And this is a classic distributed computing problem that you study, and it's what is starting to become kind of the forefront of these cloud scaling challenges we're looking at. Likewise, questions about storage, where I'm storing and why, may be totally separate from interaction. Right? We tend to think about the database as the whole stack, as the place where I'm interacting with the data and the place where I'm storing the data. Right? Because that's that original system R design. That's that vertical scale that we've been used to for decades in our industry. Right? But this one right here is a great example of sometimes where I store the data is an orthogonal question from where I want to be accessing it and why. Right? And as we want to be able to build cloud scale architectures that are working across multiple geographies, this becomes a really important, interesting question to ask. What I'm really saying is, we had this architecture, this kind of scale up, vertical scale architecture that's really predicated on the disk, that you can make scale by making the disk kind of a bigger thing that a few more things can access, right? But they're so evolving. We've tried this architecture that is really more about sharding or replication, kind of separating the world, right? And to get to the next level of these architectures, what we need is we need architectures that think about all of these problems from this distributed point of view, solving the problems that I just talked about, that John was talking about, fundamentally, foundationally in the architecture, that are thinking more about kind of these issues of what's in memory, what's on disk, and how the system naturally is replicated. If you read that white paper that we were handing out here, or if you go to our website, or you come talk to any of us afterwards, we'll talk to you about what NuoDB is and what our architecture is. And at a really high level, you're looking at an architecture diagram for NuoDB. NuoDB is a peer-to-peer system. It's a distributed system where every peer is independent, where every peer is capable of doing exactly the same workload, where a single logical database, no sharding, no replication, what looks to the developer like just a database with a single connection string, is made up of one or more peer processes. Because each peer process is completely independent, you can add a new peer at any point in time, a peer can fail at any point in time. And the only difference between these peers is that we separate, when we say some peers are responsible for running in memory and only in memory, and driving transactions and speaking SQL and doing all those other things, but their job is about processing. And other peers are focused on data durability. They don't care how transactions run, they don't care about the ACNI and ACID, they don't care about any kind of protocols to a client. They're there to handle data durability and provide access to durable data when it's needed. These pieces can be scaled independently. They can be run in multiple locations. Those in-memory pieces are forming caches on demand. And all of our protocols internally react to where data lives in cache. And so if you have disjoint operations that you're doing in multiple data centers, this is a system that is still transactionally consistent on a global scale as you scale across geographies, but is giving you land latency performance numbers. And that's kind of the goal of this architecture. And it's designed with all those other pieces I talked about earlier, with a security model, with a monitoring model, with an orchestration tier that gives you provisioning, gives you management out of the box as a single logical component, right? It has the interfaces for the operators, it has the interfaces for the DBAs, it has the interfaces for the developers. All of those users can still collaborate with each other, but now I write an application, and if something fails in the database, the application keeps going. Since we're running out of time, I'm just going to say there are lots of examples out there I can cite of how you use the software. If you go to Google, you can find this amusing video we did with Google when Google Cloud Engine first showed up. They gave us access to some of their early beta systems and said, kind of, what can you do with a whole bunch of our servers? And so this is a NuoDB database live, scaling from 0 GCE instances up to 32 GCE instances, running one of the Yahoo standard benchmarks, hitting about 1.8 million transactions per second on demand. And this video is really entertaining because like 5 minutes in, just as I'm handing it off to an engineer to actually start the demo, the Wi-Fi goes down at the Google campus, and we're like, what do we do? So it's a fun one to watch. Another example, just since I have it here, this is, I spun up just before breakfast, I spun up our software. So this is our standard kind of management tool that we provide out of the box. Just a web GUI, sits on top of REST APIs that you can script, sits on top of other interfaces. This is live, and this is showing you that from a single place, I can do kind of standard operations monitoring of instances. So I'm seeing information about host utilization in terms of memory, in terms of CPU, in terms of network utilization. But this is live on Amazon, and this is actually running in Virginia, and in California, and in Frankfurt, Germany. And among other things, what I've got here is I've got the view of a single logical database, not running any load against it at the moment, but I've got a view of a single logical database that I can address. It's called test. It has just a JVC connection string, but it's running in all these places. And if you drill in, you're able to see that it's made up of you can see that it's made up of a whole lot of processes running in a whole lot of places. But that kind of doesn't matter. What matters is that it's just a database. And it's a database I can just watch from a single point of view, and I can work with from a single point of view. And that gets you towards that model of resiliency, that model of scale out, that model of availability that I think is pretty critical as we push cloud architectures. So, in summary, I think when you're trying to architect for the cloud, I think what I heard, I'll try to channel John as well and just say, I think what we're really talking about is looking for architectures with on-demand capabilities, thinking about layering abstraction so you can handle failures effectively, so you can really think about how to separate your components, to be able to swap in things as you need them. Assuming that your needs will evolve, and plan to evolve with that in mind. And I would encourage everyone to go check out NuoDB. You can download it for free from our website. It's just a piece of software, Mac, Linux, Windows. You can take it for a spin. I think I'll open it up to a few questions for John and me if anyone has them. So thank you. Yeah.
Just one question. Would you say you're advising people on how to architect for the cloud or how to architect for the clouds, given that there are vendors and vendor uniqueness and the monitoring and control that you want to retain versus a lot of dependence on vendor specifics? What do you say to the folks that are trying to design, not get locked in, take advantage of the things that you're saying?
No, I think that's a great question. I'm sure I'll let John also give his view on that. I mean, my view on it is the people we're talking with are people who are doing exactly what you're describing. They're people who do not want to tie themselves to something specific. They're often starting with a single public cloud in mind, or they're often starting with something like OpenStack or something internal that they're targeting. But they're almost all people who understand that they don't want to tie themselves to a particular stack, they don't want to tie themselves to a particular monitoring model. And I think that is part of the challenge. Part of the reason we chose to build a SQL database is because that's a really great place to start if you want something that is generic and is not tying you to something, to a specific architecture, to a specific operating system, to a specific language. But I think that is one of the hard questions. Is that as an industry we have not gotten to the point yet where there are standard APIs where everyone speaks the RFC 9237 API for monitoring infrastructure as a service. And we may get there eventually, but until we do, that is one of the challenges of how do you balance solving a real problem with recognizing that there may be different places you want to work for different reasons. I speak to people all the time who are like, well, I really like Amazon for the developer friendliness. I really like SoftLayer for the infrastructure it's giving me. I really like ThingX because they actually have a data center local in my city. Right? It's like, what should I do? And that is, I don't know, John, you have any thoughts about that?
Yeah, I'm a Gemini, so I have two thoughts about it, and I go back and forth, and it's really situational. In a lot of cases, we absolutely like the idea of cloud independence and vendor independence, being able to have your application not tied to a particular cloud platform, so you don't use a ton of the built-in native proprietary services, but you focus on things that are common and standard, like VMs and using an independent database as opposed to one that comes with a cloud. But on the same side, right, or on the other side, there are a lot of services that are in these clouds that you take advantage of because they're quick and your focus is more on agility than on portability, right? So, you could deploy a Hadoop cluster yourself on Amazon, or you can use Elastic MapReduce, right? I do think in the case of there's a lot of things going on in databases at the major cloud providers. There's some uniqueness and interesting aspects to what NuoDB is doing, which changes the game a little bit, specifically in the context of hybrid cloud. I might want to run my application distributed, where some of my core system is running internally, and maybe that's where my database, kind of core database on disk on record, but I did multiples of those. If I have that running there, and then I've got the in-memory versions and other things spinning up to handle elastic demand curves in public clouds, right? So that's the old utility model. If you've ever if you've read it, I feel sorry for you, but know about Joe Wyman's book on cloudonomics. Joe is a fantastically brilliant guy, but he lays out the formulas for how you determine why elasticity and having a fixed base and elastic up and down is great. So an example of that would be eBay. I saw a talk a few years ago by somebody at eBay, CTO I think, and he was talking about how there's like 2,000 servers in the primary eBay server farm. And what their goal was to move down to 800 servers in their server farm and put 1,200 of those servers, if you will, elastically into Amazon, so that, because really at the end of the day they have very spiky demand. And so when you do that, then you start dealing with how do I handle a database that spans my internal private cloud and then the service catalog of Amazon or Google or Microsoft Azure and their databases. So that's hard. So there are things that you want to bring with you, but there are other things that are really, if you're trying to move really, really fast and you're prototyping and doing stuff, that you might want to use what's native in that cloud. So the answer is, it depends. But I used to say, don't get yourself locked in. I more say right now, focus on, if you're building something new, what's the most agile way for you to do it? And you use some things, and don't be afraid of getting locked in. So don't be afraid of, it's a SQL database. It's not that much of a lock-in, but don't be afraid to get locked into a database that's going to work for you. If you're worried about that, just go ahead, go for it. Go for using SQS if you're going to run everything on Amazon when you get started for a queue system or SMS for messaging. It's okay. Those things are hard to deploy and manage yourself. And the old saw of the cheapest code, line of code to maintain is the one that you never wrote in the first place. So, if you're putting out things that are, you're managing RabbitMQ yourself and you're managing a whole bunch of other things, it just increases your operational complexity. I don't know if that answers your question.
One more question? Or, yes?
Between your experience of answering the question, I want to move to AWS and get out of my DC, what don't I know? If you had to categorize what the general reactions are to your recommendations, is it, and people either don't proceed or proceed in an avenue that isn't optimal in your view, is the holdback technology, is the holdback financial, or security?
Again, it depends, but I think what we're seeing is that attitudes are changing on security. Not, there was a speaker at Cloud Connect a few years back who said, started with the cloud is here, right? The future is here, it's just not evenly distributed. So there was a CIO at a top 5 bank that I was working with doing a strategy project in 2012, who told me there was no way that they were going to be migrating any applications to Amazon. They were building a private cloud, and that's all they're going to do, because for security reasons, right? We've now moved one of the data centers to Amazon. All the test and some production applications as well. So things change from that standpoint. The biggest thing that people don't know, right, that they think they know, is on the operations side. I can do this. I got smart people. We know how to operate things, right? Because we operate things today. We operate big scalable applications today. We're a bank. We know how to do this. The issue is that all the people that you have, right, they look kind of like us, right? You're at a bank, been there for a while. There's some young guys running around, but there's a lot of people kind of, mid-career, handling core strategic things, and they know how to do what they know how to do. But a lot of this stuff is new, right? All the monitoring tools, the way you secure things, how you manage that. So we go in and do audits of people's Amazon environments, and do security audits and other things. It's not that Amazon's insecure, they just don't know what they're doing. So there's that old saying that there was a clothing retailer, Sims or something like that, an educated consumer is our best customer. For those of you around here, you will have heard that ad before. People that have tried it and failed are, my perfect client, because they actually have stopped believing that they're superhuman and can do everything, and they realize that they do need help. And so it is complex from an operations perspective, and but when you tell people you don't know how to do this, we don't use those words, of course, but when you try to lead them down that path, unless they actually have done it before, they don't believe it. So if somebody hasn't tried it before, I actually encourage them to go ahead and try it and then call me.
Knock yourself out.
Yeah, knock yourself out.
All right. Thanks, everyone.
Thank you.